Well, seeing as we've got someone watching, we might as well get started, eh? Let's get started. Let's just play a bit to begin with. Okie dokie. There we go. So it went up to like 5 viewers for a moment, and then it stopped. Oh, 3 viewers. There's someone. That was pointless. No, there we are. Let's just start again, shall we? Okie dokie. Nope. Okay, and there we are. That's always good. Yep. Okie dokie. So we've got 3 views now, which is good. Oh, that was not helpful. That's fun. Okay, so we've got some more people watching. Let's get into it. Let's go back to the menu and we'll start at the beginning. If you can't hear me, do say something in chat if you can. And I'll do what I can to sort that out. But you should be able to hear me. Hopefully. So, when we have a look at Angry Birds, we can see like you've got a projectile and you have to fire it in order to hit into something. One of the really nice things about Angry Birds is, if you see here, I fire it off, and I'm going to purposely miss so that it doesn't just go to the next level. We fire it, and we actually have that tracked position sitting there, which is really quite nice. That track that's there, that's showing where the bird went, that's perfect for figuring out projectile motion, figuring out where you want it to land, all of those kinds of things, how fast it goes, all of that. So let's begin with the basics. if we go over here and we start to draw out the scenario. So we've got that, and we've got the sort of whatever's being built. You've got your pig there, and then you have your slingshot and your bird. So now we need to think about what are we actually looking at. If we think about physics in generally when we think about mechanics, some of the really important ones are velocity, time, and from these we can start to figure out the other things that we might need to think about. So we want to know what units are being used. Now I'm going to use metric units because that works nicely. So for velocity, that's meters per second. Now that means that the units we're actually looking at are meters and seconds, and then with time, again, we're still just using one of the units from above, seconds. So then we can point that up to there. So using that logic, using that reasoning, what we need to know about are distances. So we could look at, let's say, the distance from here to here, and we want to know the amount of time that it takes for the bird to travel to that point. So we'll start with a simple two-dimensional system. So, one-dimensional system. At the moment this is 2 dimensions because we've got up and we've got sideways. If we break that down, however, we can instead just start with a one-dimensional system. So let's say we're just looking at the bird and seeing how long it takes for it to get from point A to point B, and just looking at that distance. So if we think about how far the bird was from the object, let's estimate it. Let's just say that it's about 3 meters, let's say. So we've got 3 meters. Now, if we figure out how much time it takes to get there, we've got everything we need. So let's say it takes 3 seconds to actually reach the object, or the point that you're worried about. So that means that then we can figure out what the velocity is, because all it is the number of meters divided by the number of seconds. So here, in this case, we end up getting 3 meters divided by 3 seconds, which then is equal to, so 3 divided by 3 and then meters per second is just 1 meter per second. So now we've got a nice distance. We've got distance, we've got velocity. The only thing we don't have is another variable which comes in handy here, which is acceleration. Which all it's measuring is how much the velocity is changing per second. So therefore, its velocity per second, or what we can do is we can use what's called a delta, which means change in. So change in velocity over seconds, which is the same as change in meters per second, all over seconds. And when you have something when you have a fraction divided by something, if it's on the bottom, so let's say we have 1/4 divided by 4, that's the exact same as 1/4 times 4. If in comparison we had a fraction on the bottom, so let's say we had 1/1/4, that would be the same as bringing the 4 up to the top, and then you end up getting 4/1. But that's math stuff. It's a different matter, although physics is basically just applied maths. So so you've got the meters per second, and then that ends up going to change in meters over seconds times seconds, and when you have something multiplied by itself, it just becomes squared. So meters per second squared. And then, of course, so we've already discussed distance. So those are the 4 things we really need to think about if we're looking at projectiles and projectile motion. So let's get rid of all this stuff so we can clear it off. There we are, and we'll keep these up here. Distance, which is in meters, velocity, which is meters per second, acceleration, which is meters per second squared, and then time, which is seconds. So let's go back to the Angry Bird. The Angry Birds. So we come back in here, and let's have a think about this. So let's say this distance from here to here, if we measure it, if we assume that each bird is maybe let's say 10 centimeters wide, and let's guess, so about 1, 2, 3, 4, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Let's say this point here is about 20 birds away, which if they're 10 centimeters each, that'd be 20 times 10, which is just 200, which in regards centimeters to meters, you have 100 centimeters in a meter, therefore that's going to be 2 meters. So we can then go back, so our distance here, in at least this dimension, is going to be 2 meters. So the other thing we can probably measure is how long it takes to move from point A to point B. So if we go back again, we can record how much time it takes. So I'm just going to use the old 1/1000, 2/1000 because we're not going to need to be too accurate with this. But let's just fire it dead straight, and we'll see. 1/1000, so it's about 1 second before it gets there. So that's 1 second. then we have, then from that we can calculate that velocity is equal to 2 meters over 1 second, which is equal to 2 meters per second. Now remember, this velocity is only in that straightforward direction. So what we can do is we can call that horizontal. So v horizontal. The velocity in the horizontal direction. Now, one thing, when you think about the acceleration, what is that actually going to be? So if we think about, let's say you've got a person standing there, actually we'll do that on a new layer. Let's say you've got a person standing there, and they're holding a ball of some sort, and then they let go of it and the ball begins to fall. Now there you've got some sort of acceleration because the speed at which something is moving has gone from 0 meters per second while he was holding it to some number of meters per second when it's dropped. However, there's nothing that's causing it to go horizontal. There's no acceleration horizontally, there's only acceleration vertically. And that, if you're not aware, is gravity. The thing that makes sure that we don't go flying off into space. Now, the value for gravity does change sort of depending on where you are in the world. It's to do with how the world isn't actually a complete sphere, it's more sort of a kind of squished sphere. Can't quite remember which way in which it's squished, but it's squished in one of the ways. But I'll use gravity down here in New Zealand, which is 9.81 meters per second per second. But again, this is only in the vertical direction. Is there anything at all that would change the acceleration in the horizontal direction? Now this is where you get to a wee little trick that physics tends to do, which is basically that we don't worry about friction a lot of the time because it makes the maths difficult. So, if there's no friction, there's no air resistance, nothing pushing against it to try and slow it down, that acceleration is going to always be 0. So we have all of the horizontal values, and now the question comes in, so we have time. Is time in any way part of space? Is it in any way a distance? It is, but not in a spatial dimension kind of thing. So there's all the stuff we see, what we move around in. We exist within a three-dimensional space, and then the fourth dimension is time. So let's say you've got this box here. In one moment it's like this, and then maybe the next moment it's just been squished, and so now it's smaller, and so time has passed. But time doesn't care about how it looks different. All it knows is that time has passed. As such, time becomes the thing that you can then use to figure out all the vertical and horizontal stuff. So, we know that the vertical acceleration is going to be equal to 9.81. And so we have that value there. So AV equals 9.81 meters per second squared. So now all we have to worry about is V vertical and D vertical. So now this is something to bear in mind. The distance is always going to be a change in. So remember, the delta symbol means change in. And so normally with just a two-dimensional system, we'd be using V equals change in D over T, change in distance over time, and then acceleration would be change in velocity over time. That only works with just the straightforward forward and back one-dimensional system. So in comparison here, we have to think a little bit differently. We have to use things that are a little bit fancier. However, they all come from these equations. So, for example, V is equal to... No, we won't use that one to begin with, actually. And we'll use a bit of a larger eraser. There we are. We'll look at the acceleration. So acceleration, we've got delta V over T. The thing is, delta V, if that's the change in velocity, that's the same as the initial velocity minus the final velocity. So this acceleration then ends up becoming the initial velocity minus the final velocity all over time, which brings us into the equations that we'd be using for this stuff, which are called kinematic equations. Now, this particular equation does get rearranged a little bit, so we end up getting the A equals Vi minus Vf over T. And if we rearrange that to get rid of this fraction here, so whatever we do on one side, we do on the other side. So let's multiply both sides by t. So we end up getting AT equals Vi minus Vf. And it's technically over t all times by t, but the two t's cancel each other out, because if you have a number divided by itself, it equals 1 and just disappears. So we can just have it like so. And then we end up getting closer to what the actual kinematic equation they use is, which becomes, so if we get rid of this negative here by adding Vf to both sides, we end up getting Vi equals Vf plus At. Now this here is the first of 4 equations that will basically allow you to figure out whatever you want. We can then figure out all the other stuff using the same information. So let's we will just write that last equation up. So we had Vf equals, well, did we? Wait a minute. Did we do that right? Oh, no, sorry, my mistake. Always good to learn to have mistakes, because getting things right only tells you that you're correct. Getting things wrong tells you a hell of a lot more. Anyhow, so yes, sorry. That should be switched around. The reason being, so you actually take the final value. So let's say at the end of a race you were going 100 meters per second. Pretty fast, yes, but probably realistic actually for race cars. So you're going 100 meters per second. At the start of the race you were going 0. Therefore the change that occurred was in fact 100 meters per second. Positive, because you increased to 100 meters per second. That's why that should be there. That was my mistake. Therefore, let's just get rid of all of that. Clear that out. And then we can also change that to initial. So the initial velocity was equal to the final velocity plus the acceleration times the time. Now we can have a look at something like the so velocity is equal to distance over time, the change in distance. Thing is, now this velocity here, that's not the velocity at every single point of a journey. So let's say we had a graph and we had the velocity go like that. What we're actually getting with this here is we're just getting what the average velocity is. So it's probably somewhere around there, as if the velocity were the same the whole way through. And how do we get averages? You take, if it's just a nice clean average, you take, let's say we have some items and then some other items, and we wanted to get the average number of items in each section. We would go, okay, 3 plus 5, and then we would divide that through by 2, because 3 items in the first one, 5 in the second one, and then there are 2 total groups overall, which that ends up being 8 over 2, which then equals 4. So the average number of items in each of these is 4. We'll get rid of that. So if we use the same logic, we have the initial velocity plus the final velocity, all divided by 2, because we have 2 values here. That would be that would be equal to the change in distance over time. And then we can rearrange this once more to get the equation that we usually have. So we want to get, let's say, the distance by itself. So then we multiply both sides by time, as we saw before. So we end up getting change in distance is equal to initial velocity plus final velocity over 2, all multiplied by time. Now these are the first two, the easiest two to figure out. I will happily leave you to figure out the other 2 kinematic equations, and what we'll do now is I'll just write up those other 2 equations so that we can get into actually figuring out how all those angry birds were moving. Sorry, that did take a little while, but wanted to make sure that people understood the basics, because obviously I don't know where people are coming from with this. Best to start early and then get into the more advanced stuff. So let's say, so the other 2 kinematic equations are distance is equal to initial velocity times time plus a half acceleration times time squared. And then the other one is velocity final squared is the initial velocity squared plus 2 times the acceleration times the distance. And so these are the equations that we'll have. So if I remember correctly, we had, so the distance in the horizontal direction was equal to 2 meters. The velocity in the horizontal direction, the average velocity in the horizontal direction was 2 meters per second. and the acceleration, because we were like, nah, we won't worry about friction or anything like that because that makes things messy. That's 0 meters per second squared, and the time was 1 second. Nice easy numbers. Then we had, so vertically, our distance vertically, we didn't know. The velocity vertically, we also didn't know. Acceleration is vertically, if you're on the planet, is always going to be gravity, and here in New Zealand that is 9.81 meters per second squared, and the time is the same in both cases because it's not related to distances. So now we can figure out what all these different ones are. So let's say we want to figure out the distance in the vertical section. Now that's the thing, you can't use the horizontal distance to calculate the vertical distance because they are separate things. So what we need to do is we need to find something wherein we can get distance. Now if we look at all of these equations, if there's distance, there's always going to be at least 3 other variables. We want to ignore velocity as much as we can. Now, because we fired off the bird just straight that way, that means we weren't pointing it up, we weren't pointing it down. We can say that the initial velocity in that direction was, in the vertical direction, was 0 meters per second. I'll leave the whole vector calculation-y stuff for now, because I think I've gone into that a bit too much. But, yeah, so you've got the 0 meters per second in the vertical direction, whereas that horizontal is 2 meters per second. You'll notice sometimes I use to the -1 and sometimes I use over. They're the exact same thing, because to the -1 means it's divided by that value, and then having it as a fraction, it's divided by that value. So let's get to it. Yeah, so that is our initial velocity in the vertical direction. Bearing that in mind, we can now look at this and go, okay, where's one which figures out d, has initial velocity, has time, and has acceleration? So it'll be that one. So that ends up being d equals v I t plus 1/2 a t squared, and now we just plug the numbers in. So d is equal to, so vi is 0, that's 0 times 1, plus a half times 9.81 times 1 squared. Now 1 squared, that's a nice easy one. 1 times 1 is 1, because if you have one lot of 1, you have 1. So then anything times 0 gets cancelled out, so that gets removed. So we end up getting d is equal to a half times 9.81 times 1, but times 1 is a redundant statement, therefore it's just going to be equal to that, which is equal to a half of 9.81, which half of 9 is 4.5, half of 8 is 4, so that ends up being 4.905 meters. However, I feel like something has gone horribly, horribly wrong now, because that's way more distance than you would have thought, given that it fell. What that suggests, then, is that the rate at which it falls is not in fact gravity. Given that if we go back to Angry Birds, that distance is closer, in fact, to, or maybe a fifth. That height there is maybe a fifth of the distance that travels. We then realize, okay, it's actually not using Earth gravity. So, important part of science is always questioning things. In this case, the question is, okay, what gravity do these angry birds live on? Let's figure that out. If we assume, so we'll get rid of this section because this was clearly wrong, because when we looked at it, it's wrong. If we instead assume that the vertical distance is a fifth of that, so 2 over 5 meters, which is, so 1/5 is 0.2, therefore that's equal to 0.4 meters, and we assume that this is in fact incorrect. Now we can do it again, but just with the different numbers. So we have d equals VIT plus half AT squared. And we can first plug in the numbers. Always, if you can, plug in the numbers first. So 0.4 equals 0, because again the VI times, the 0 times anything becomes 0, plus a half A times 1 squared, which again that cancels out, nice and easy. So all we need to do is we have 0.4 equals a half A. So if we want to get rid of this half on this side, we just divide both sides by a half, and dividing by a half is the same as doubling. Therefore it's 0.4 times 2 equals A. Therefore our vertical acceleration in this world is actually 0.8 meters per second per second. So if we think about it like that, we've got we've now just looked at a situation and we've gone, this is not actually working how I thought it would. Let's figure it all out, figure out how this is going to be different, all of that, and then we've found out how it works. This can be applied to basically anything. So you could play any video game that you're interested in. Let's say you play Skyrim. So in Skyrim you've got those bits where there's the falling boulders and all that, and then it releases it and they all fall down, and if you're smart they generally don't hit you. But when they come off of this point here, you could easily time how long that took, and you could figure out, okay, this is what the gravity is here. You can take a skill like that and you can actually apply it to sort of celestial mechanics, so planets and all of that kind of stuff. Because thinking, if you know what the gravity is, then you can figure out what the total mass of the planet is, because gravity is proportional to mass. If you've got a larger planet, you've got more gravity holding you there, and so you could use that to figure out how heavy a planet is. We won't do that at the moment. I will leave it at that for now. If you have any suggestions whatsoever, I have created a Discord server for people to sort of put stuff together and ask what they're thinking. And yeah, I will actually let's figure this out, because I might be able to put the Discord server name into the chat. Just give me a moment. So Discord server, Yep. Let's. There we are. So I should be able to put that into the link, into the chat. And so if you have any ideas for things to cover, anything at all, while most of us around the world at the moment are staying at home, just put it in there, and yeah, I will leave it at that for now, and hopefully we'll see plenty more people coming along to have some fun. Goodbye, and stay safe out there. Okay.